Bismillah ar-Rahman ar-Rahim. We have a sequence of complex numbers C1, C2, C3, and so on. And then this sequence converges to the complex number C. So limit as n tends to infinity of Cn is equal to C. Our goal is to show that the limit as n tends to infinity of 1 plus Cn divided by n all raised to the power n is e to the power c, which is the same c. Now, because the sequence Cn is convergent, then it is a bounded sequence. So it means that the magnitude of Cn for every positive integer n is less than or equal to some finite positive real number big M. Now, we can use this to show that the limit as n tends to infinity of magnitude Cn divided by n, that this is 0. And we can do it by the sandwich theorem. This magnitude divided by n is non-negative. And since the sequence is a bounded sequence, so the magnitude of Cn is less than or equal to big M. So this limit, or this quantity here, the magnitude of Cn divided by n, is less than or equal to m divided by n and is greater than or equal to 0. Now we take the limit. This side, the limit is 0 as n tends to infinity. That side as n tends to infinity. And because m is some given finite number, the limit will also be 0. So the limit of this quantity exists as n tends to infinity and is exactly 0. The limit is 0. It means that this quantity can be made arbitrarily small by choosing a large enough n. So for a large enough n, we have the magnitude of Cn divided by n is less than 1. So we can choose n. There is a threshold such that if n is greater than or equal to that threshold, the magnitude of Cn divided by n will be less than 1. In fact, it can be made less than any arbitrary positive number. We will choose this number to be 1. Let's investigate the magnitude of a to the n minus b to the n. And those are complex numbers. So we know that a to the n minus b to the n is equal to a minus b. And then we have a to the power n minus 1 plus a to the power n minus 2 times b plus a to the power n minus 3 times b squared. And then we have a times b to the n minus 2 plus b to the n minus 1. So we can write down this bracket here as a sum j from 0 to n minus 1, a to the j, b to the power n minus 1 minus j. So if j is 0, we have this term here. If j is equal to 1, we have this term here. If j is equal to small n minus 1, we have this term here. Now we want to upper bound. So the magnitude, of course, of this product is the magnitude of a minus b times the magnitude of the sum. And so we can employ the triangle inequality. We can upper bound the magnitude of the sum by the sum of the magnitudes. Now we can upper bound magnitude A and magnitude B. We can upper bound each one of them by the maximum of the two magnitudes. And then when we do this, this maximum and this maximum can be combined. The power here is j, the power here is n minus 1 minus j. And now we have this is upper bounded by the maximum of the magnitude of A, magnitude of B raised to the power n minus 1. And then we can multiply by the number of terms in this sum. And this is a summation with n terms. So the magnitude of A to the power n minus B to the power n can be upper bounded by n, the magnitude of A minus B, and then the maximum of the magnitude of A and the magnitude of B raised to the power small n minus 1. We take this inequality here and apply it to the magnitude of 1 plus Cn over n all to the power n minus e to the power Cn. And this e to the power Cn can be written as e to the power Cn divided by n, all raised to the power n. So here we have, like, this is a to the n minus b to the n. Now, what is the goal? The goal is to show that this magnitude here is less than any arbitrary positive number. So this magnitude is less than, so goal is to show that this is less than epsilon for every strictly positive epsilon. And if this statement is true, then the limit of this magnitude as n tends to infinity is equal to 0, because the magnitude can be made arbitrarily small. And if the limit of the magnitude is equal to 0, then the limit as n tends to infinity of 1 plus Cn over n all to the power n minus e to the power Cn, then the limit of this quantity is also equal to 0. So this includes, this is our quantity of interest, and then the other term is limit n tends to infinity e to the power Cn. Now, Cn, it's a given that Cn is a sequence that converges to the complex number C. And because the exponential function is a continuous function, then limit n tends to infinity e to the power Cn is actually e to the power C, and we are done. So now the main part of this derivation here is to show that this quantity can be made arbitrarily small. Given any epsilon that is strictly positive, I can make this quantity to be smaller than epsilon by choosing small n to be large enough. Our starting point will be to employ this bound that we have here. And so this magnitude is upper bounded by n. So the power here n and n, so we have n, and then the magnitude of the difference between 1 plus Cn over n and e to the power Cn over n. And then we take the maximum of the magnitude of 1 plus Cn over n and the magnitude of e to the Cn over n. Now to proceed, we need an upper bound on this quantity. Now this quantity can be, of course, the magnitude, the magnitude of a complex number is like the magnitude of its negative. And so we are interested in something in this form. The magnitude of e to the b here is Cn over n minus 1 plus b. So we are interested in doing this, basically writing down or obtaining an upper bound on the magnitude of this difference, where b is a general complex number. Now, do the Taylor series expansion of e to the b, and basically this minus 1 minus b means that this quantity has this expansion, summation j from 2 to infinity, b to the j over the factorial of j. Again, employ the triangle inequality, which means that the magnitude of the sum is less than or equal to the sum of the magnitudes. Now, the factorial of j, which can be written as those j minus 1 terms, 2 times 3 times 4, all the way to j. So this is the factorial of j. Now, you can lower bound each one of those guys by 2. So for j that is greater than or equal to 2, we have factorial of j is lower bounded by 2 times 2 times 2. Each one of those terms can be lower bounded by 2. And we have j minus 1 of these. And so for j greater than or equal to 2, we have the factorial of j is superior to 2 to the power j minus 1. Taking the reciprocal of both sides, then 1 over the factorial of j is upper bounded by 1 over 2 to the g minus 1. So the first upper bounding step here is using the triangle inequality, and then for j greater than or equal to 2, 1 over the factorial of j is less than or equal to 1 over 2 to the j minus 1. We can multiply so that we have 2 to the power j, and so we can have magnitude b over 2 all to the power j, and then we will have an external 2 here. This is a geometric series, but to be convergent, we will need that magnitude of b to be strictly less than 2. And with this choice, the sum will be magnitude b over 2 to the power 2 over 1 minus the ratio of the geometric series, which is magnitude b over 2. And this is magnitude b squared divided by 2 minus the magnitude of b. We insist that magnitude of b is less than 1 rather than being less than 2. We will say, well, what if it's less than 1? Then minus the magnitude of b is greater than minus 1. Add 2 to both sides, then 2 minus the magnitude of b is greater than 1. Taking the reciprocal of both sides, then 1 over 2 minus the magnitude of b is less than 1. And so the magnitude of b squared over 2 minus the magnitude of b is less than or equal to the magnitude of b squared. And this is true if the magnitude of b is less than 1. And this condition will also ensure that this geometric series is convergent. So now we have this auxiliary result that for b being a complex number, and if the magnitude of b is less than 1, then the magnitude of e to the b minus 1 plus b, so this is the difference between e to the b and the first two terms in its Taylor series, 1 plus b. The magnitude of this difference is less than or equal to the magnitude of b squared. And we can apply this result to make an upper bound here. So the magnitude of e to the c over n minus 1 plus cn over n, this magnitude is upper bounded by the magnitude of this quantity squared. So this is the magnitude of cn squared divided by n squared. Now, is this justified? Note that our upper bound here is when the magnitude of b is less than 1. But for n that is large enough, the magnitude of cn over n is less than 1. Remember, because that cn converges to c, so cn is a bounded sequence, and so the limit as n tends to infinity of magnitude cn over n is equal to 0. By choosing n to be large enough, this quantity can be made arbitrarily small, and so we can choose a large enough n so that this magnitude of cn over n is less than 1, and then we are justified in applying this result to this magnitude here. Magnitude of 1 plus cn over n by the triangle inequality, this is less than or equal to 1 plus the magnitude of cn over n. Now, the magnitude of e to the cn over n is less than or equal to e to the power the magnitude of cn over n. So if z is a complex number, it has a magnitude of z and an angular argument theta, e to the I theta, then what is the magnitude of e to the z? So it is the magnitude of e, and z can be written as the magnitude of z cosine theta plus I, the magnitude of z sine theta by Euler's identity. Now the magnitude of e to the I magnitude z sine theta, note that sine theta is in R, this magnitude, so this is a number, a complex number living on the unit circle, and so the magnitude is equal to 1, and the magnitude of this quantity will be e to the magnitude of z cosine theta, which is a positive real number. And what do we have here? The magnitude of z cosine theta. Well, cosine theta is less than or equal to 1, and so this is upper bounded by e to the magnitude of zeta. So the magnitude of e to the z for any complex number z is less than or equal to e to the power the magnitude of z. And so this magnitude here can be upper bounded by e to the power the magnitude of cn divided by n. And we also know that if we have a real number alpha here, then e to the alpha is greater than or equal to 1 plus alpha, which means that 1 plus magnitude Cn over n, this is less than or equal to e to the power of the magnitude Cn over n, which means that those two terms here, both of them can be upper bounded by e to the power of the magnitude of Cn over n. And so we can just, rather than using this maximum, we can use e to the power of the magnitude of Cn over n, and it's raised to n minus 1. And this can be upper bounded by e to the magnitude of Cn because n minus 1 over n is less than 1. The magnitude of 1 plus Cn over n all to the power n minus e to the Cn now is upper bounded by 1 over n, the magnitude of Cn squared, e to the power of the magnitude of Cn. And note that Cn is a convergent sequence, so it is bounded, and every term in that sequence in magnitude is bounded by this finite positive number big M. And so this upper bound is less than or equal to 1 over n, m squared e to the power m. And this quantity can be made arbitrarily small. Given any strictly positive epsilon, then by choosing n to be greater than or equal to 1 over epsilon m squared e to the m, we can make this upper bound less than epsilon, and so this magnitude is less than epsilon. This quantity, for every epsilon greater than 0, this magnitude here is less than epsilon for sufficiently large n. And this is exactly the meaning that a quantity tends to 0 as n tends to infinity. Okay. So this limit is equal to 0. Now our objective is realized, because if this limit is 0, then the limit of this complex valued quantity is equal to 0. Now e is a continuous function, so e to the Cn will converge to e to the c as n goes to infinity. So the limit n tends to infinity of 1 plus Cn over n all to the power n is e to the c when Cn converges to c as n tends to infinity.